Hello. Okay. Okay. Now, hello students. My name is Sumit Sagar Hota. I am a PMRA PhD scholar IIT Palakkad. Today we will discuss lecture 55 to lecture 60 by Professor Ashok Des Sir, IIT Kanpur, of the subject Introduction to Air Breathing and Propulsion by NPTEL. This is the week 12 of the live discussion section. In this section, we will cover some of the MCQ questions, mostly MCQ questions are there, and some of the problems. Okay. In this section, MCQ questions are also high. Okay, so you should focus also on the what MCQ questions as well as problems. So how many burners are placed in a can annular combustor in gas turbine? Okay. So the answer is D. Not specific. One or more. Okay. Does it mean multiple or single burners are evenly spaced in the combustor? Okay. Silo combustors are mounted internal to the gas turbine body. Okay. Answer is what? False. Okay, it's not internal, it is external. Mounted external to the gas turbine body. Okay. Axial flow turbines are used in what? Industrial gas turbine. Okay. Axial flow turbines are always used as the industrial gas turbines. Okay. Okay. What completes a stage in the turbine expansion? Okay. Okay, so stage means what? One, there is one stationary blades row, and as well as there is one what? Moving blades row. Okay. What does TRIT in a gas turbine stands for? Okay. TRIT, turbine rotor inlet temperature. Turbine rotor inlet temperature. Okay, if it is TIT given, then turbine inlet temperature. Okay, get it? So now next question. Whatever. When at ideal condition, gas turbine engine use more fuel when compared to reciprocating engines. Okay, A is the true. Okay. At ideal condition, the gas turbine engine use more fuel when compared to what? Reciprocating engine. Though the condition may be at ideal, born to run the turbine compressor to work, compressor takes as much as 2/3 of the total power produced from the combustion and remaining 1/3 used for the power output. So during the ideal condition, the power output may not be required, but compressor uses its 2/3 of the energy. Whereas reciprocating engines does not require any compressor equipped separately, and hence less fuel will be burned during the idle time when compared to what? Gas turbine. So this is the reason for that. Okay, already tell the reason. Okay, you can means video you can reword it or forward it like that you can do, and listen it again. Okay, I am not going to write down all this thing here. Okay, I already explained you. Okay, you just go through it. Okay. Now next question. In the gas turbine compressor, raise the pressure of air by dash times. Okay, the answer is 3. Okay, 30 times. Okay. Compressor work is to raise the pressure of the air at constant volume. What is the work of compressor? Compressor increases the what? Pressure at what? Constant volume. Okay. So in gas turbine, raises by what? 30 times. Okay. In gas turbine, the turbine is used to convert what? A. Gas turbine, the turbine is to convert the kinetic energy to what? Turbine. What is the work of gas turbine? Kinetic energy to rotational energy. This is what the work of what? Turbine. Now, next question. The radial equilibrium theory assumes that the flow is in equilibrium before and after the fluid entering the blade. Is it true? Obviously, it's true. Okay. Radial equilibrium. Okay. Flow is in equilibrium before the fluid enters and after the fluid leaving the blade. Okay. Based on type of flow arrangement, the gas turbines are classified into what? Axial flow gas turbine. Okay. Okay. So based on type of flow, the arrangements, gas turbines are classified into axial flow gas turbine. Okay. Because other options are not related to the type of flow arrangements. So in actually one is axial flow and another one is radial flow. Dash is developed when the working fluid is passed through the blade passage. Okay. When the working fluid passing through but blade passes, and due to which what happen? Friction develops. Due to friction, what will develop? Internal heat loss. Okay. The kinetic energy of working fluid is dash of kinetic energy case lossless flow. Okay, if the flow is there which is having no loss, okay, and the kinetic energy of the working fluid will be what? Okay, the kinetic energy of the case of lossless flow is lesser than the kinetic energy of the what? Working fluid. Okay. So the major objective of this question is to tell you this term lossless flow. Okay, that means the kinetic energy of working fluid is greater than the kinetic energy of the lossless flow. The ratio of actual velocity to the velocity of case lossless flow is called what? Okay. This is the definition of velocity coefficient. V square divided by B lossless. Okay. The difference between actual enthalpy of working fluid to case enthalpy of isentropic flow is called as what? Okay, so you know what is loss? The loss is the losses are the enthalpy difference between the working fluid and the cases of what? Isentropic flow. Okay, so this is the definition of what? Loss. Maybe because why this will be? Because if you working fluid minus the isentropic flow, you get the sign as what? Negative. Okay, the loss is always negative. Okay, the losses occur due to the enthalpy change is caused due to what? Okay, loss always caused due to what? Friction. Losses in flow, what will change? Enthalpy change. The velocity coefficient is applicable for what? Okay, for velocity coefficient, this is a tricky question. There is no limitation for the flow passage. Okay, that means it is applicable to all type of flow. Okay, the velocity coefficient can be applied for dash flow passage. Okay, okay, so the same way velocity coefficient does not depends on any kind of flow passage. Okay, it can be applicable for any kind of flow passage. Okay, so the answer will be D. Okay, so now velocity coefficient can be applied for dash blade passage, flow passage any, blade passage also any. Okay, the blade profile loss for a diffuser blade depends on what? Okay, there is a blade profile loss is there. Obviously that means there will be a flow involved. Okay, the flow is involved. Okay, depends on the what velocity. Okay, and if it depends on the velocity means it depends on the kinetic energy. Depends on kinetic energy. The blade profile losses are dash losses of the stages at turbo machines. Okay, the blade profile loss is always a small loss. Okay. Okay, next question. A turbine having alternate blades and nozzles is called as what? Okay, alternate blades are there and nozzles is also involved. That means it's a what? Impulse turbine. What does it mean? That your blade and nozzles arranged in alternate manner. Then what is the case? Pressure loss can be reduced. So if the pressure is reduced, then what is the name? Name will be impulse. The multi-stage arrangement of the turbine is called as what? Staging is there. Staging is also one more name is there, that is compounding. So why this is thing will be there? It reduces the pressure loss. Velocity loss. Okay. And so this is the advantage. Okay. This Because of these two things, it's called compounding. Compounding dash efficiency at low speed. Obviously, because of compounding, all the losses are reduced. If the losses are reduced, that means efficiency will increase. But it should note that it's at low speed, not at the high speed. Okay, high speed maybe condition will be different. That means it's a function of speed. Okay, depends on speed, efficiency will vary. You have to change the compounding also. It's not like for the high speed flow you will just have only two stages. Okay, and it depends on the size of the turbine, its rotor diameter, everything. Man, lots of functions are there. Okay, so staging also matters. For example, very high speed flow, you have to increase the number of staging. Okay, to increase the efficiency. In pressure compounded turbines, moving nozzles are followed by turbine blades. Okay, this is absolutely wrong statement. There is always a fixed, then there will be moving. Okay, pressure compounded turbine. The fixed nozzle followed by moving blades. In pressure compounded turbine, flow passage is from dash. Okay, same question, just true false, and then in the MCQ two ways the same question can be asked, so that thing I only show here. So pressure compounding, pressure compounded turbine. Okay, so fixed nozzle to moving blades. Okay, next question. A radial flow turbine. Okay, the question is, a radial flow turbine of the following geometry is tested under the design condition. Ratio at inlet work output after the allowance has been 1000 second, and the gas mass 3 to the tip diameter up tip, the flux angle is 5 to equal to 70 degree. for a test on the end T and the root R to be things also lambda R and beta T. So first we write down what the difference T naught 1 minus T3 dash equal to, this is directly we have the formula because P1 by P3 equal to 2 given. Okay, sorry, P naught 1 by P3 equal to 2 given. So we directly use the formula T in between the T naught 1 and T3 dash. Okay, directly, because T3 dash will be your isentropic temperature. Okay, so from there we directly find out. So which is your T naught into, because you see T naught also given 1000 Kelvin, you see 1000 Kelvin given, the inlet temperature is what 1000 Kelvin given. Okay, and this is also given, this two is enough to find out the others. Okay, so first step is required. So 1 by, if you know the formulas, then you should understand what I am writing. Gamma minus 1 by gamma. Okay, is equal to 1000 1 minus 1 by 2.0 to the power 1 by 4, 159.1 Kelvin. So now we know the difference between these two. Okay, now we know what is work done. W is equal to mcp T naught 1 minus T naught 3. In between 1 to 3, what is the work done? So T1 minus T3 we can find out from this as, because you see work done is already given 45.9 kilowatt. It's given 45.9 kilowatt. Okay, the work done. Okay, work output. So divided by all the other things already mentioned, m dot, sorry, m 0.322 m dot. Okay, m dot is 0.322 kg per second given. Okay, and Cp value is already known, or it should be given, but at the temperature, mean temperature, you can find out the Cp. Okay, most probability this should be given in the question. Okay, the answer is 124.2 Kelvin. Okay, so now take the ratio 124.2 divided by is your isentropic efficiency. Okay, actual by isentropic temperature difference is your isentropic efficiency, which is 0.781. Okay, now isentropic efficiency find out, this is your answer also. And next is your, now you know you have to, okay, so some of the things you should get from the theory. Okay, So directly we are going to see the ratio of R3 by R2. Okay, what is R3, what is R3 by R2 ratio? All these things you should get from your theory. Okay, I'm directly putting the values in the what formula. Okay, this is your what, okay, this is your hop tip ratio at the exit, that is 0.3 into, okay, into 7.85. okay, this is the formula of R3 by R2. This is already taught in the in your subject. Okay, 7.85 divided by 2 into 12.7. 2 into 12.7. 12.7 is your rotor inlet tip diameter. Okay, all things are given here. You see, this is your 12.7, this is your 7.85, and this is 0.3. okay, so some R3 by R2 and ratio is there. Okay, this is, and that is the formula I just write down. Okay, using this you can find out this ratio R3 by R2, which is 0.402. okay, and now, and eta t having also one very good formula which will relate to your what, lambda r. okay, what is lambda r? Is your rotor loss coefficient. Okay, so the rotor loss coefficient and lambda r having a very good relation, that we have to just substitute. Okay, with some angles, this nozzle efflux angle alpha 2 and beta 3, all these things are include directly in the formula, and I directly writing down the formula using the values. Okay, it should get directly. Okay, 1 plus 1 by 2 into 0.402 square, 0.402 your R3 by R2. okay, into cot square. Okay, cot square into beta 3 is your rotor vane outlet angle. Okay, is your 40 degree. Okay, plus lambda r into cosec square, and again into that beta 3 40 degree. So now it's done. Okay, okay, plus 0.07. okay, 0.07 is the model values, already the formula is there. Okay, so cosec square into 70 degrees. Okay, 70 degrees your nozzle efflux angle alpha 2. okay. And take just take the now what, inverse. If you take the inverse and solve all these things, you will get lambda r as 0.64. okay, this is your answer. Okay, the question is very simple, but you should know all the formulas, then only you can do this kind of questions. Okay, now next question. A single stage gas turbine operates at its design condition with an axial absolute flow at entry and exit from the stage. The absolute flow angles at the nozzle exit is 70 degree. At stage entry, the total pressure and temperature are 311 kilopascal and 850 Celsius respectively. just static pressure Pascal equal to static efficiency 7 and the mean axial velocity 9. The Mach number axial velocity equal to total efficiency stage reaction. And this is what the cycle looks like. Okay. Cycle for the turbine. Okay. Gas turbine. Okay. Axial flow gas turbine. Now so first of all we know what is this total to total static efficiency. So the total to that is the total to static efficiency. Okay. Eta T is equal to WT divided by Cp T naught 1 into 1 minus P3 by P naught 1 to the power gamma minus 1 by gamma. When you are solving this kind of very big questions, you should remember all this formula directly. Okay, don't derive and do it, waste your time. Okay. Specific work WT equal to eta Ts Cp P naught 1 minus P3 by P naught 1 to the power gamma minus 1 by gamma. Okay, if you solve, put all the values here. It's 0.87 into 1148 into 1123 into 1 minus 1 by 3.11. If you substitute all these things, you get 0.248 and okay. Now by solving you get 276 kilojoule per kg. What is the Mach number? So the specific work done is done. Okay, so now the second bit is so the Mach number at nozzle exit M2 is equal to C2 by square root of gamma R T2. You see the velocity triangle here. Okay, here CW3 equal to 0. Okay, and then what, u equal to, sorry, wt equal to u into cw2. Okay, so cw2 equal to wt divided by u, 276 10 to the power 3 divided by what, 500, 552 meter per second. C2 equal to cw2 divided by sin alpha 2, solve it, 588 meter per second. T2 equal to T01 minus 1 by 2 C2 square by Cp, solve it, get value was 973 Kelvin, then substitute in M2 and get M2 as 588 divided by square root of 1.33284 into 973 equal to 0.97. Now you get your Mach number. Now you can find out, go for the next bit, axial velocity. Ca is equal to C2 cos alpha 2 is equal to 200 meter per second. Okay. Now the total to total efficiency. Now the formula, 1 by eta tt equal to 1 by eta ts minus c3 square divided by 2 into wt. This is the formula you should know. 1 pi 0.87 minus 200 square 2 into 276 10 to the power 3 equal to 1.0775. Okay, so eta tt equal to 0.93. so eta tt is greater than or what, eta ts. Next bit, degree of reaction. Rx equal to 1 minus 1 by 2 Ca by u tan beta 3 minus tan beta 2. And from the velocity triangle, tan beta 3 is equal to u by Ca and tan beta 2 equal to tan alpha 2 minus u by Ca. Now substitute all these things in Rx. r is equal to 1 minus 1 by 2 ca by u into tan alpha 2. So 1 minus 200 into 0.2745 by 1000. Rx equal to 0.451. The combustion gases enter the first stage of a gas turbine at a stagnant temperature and the pressure of 1200 Kelvin and 4 bar. The rotor blade tip diameter of 0.75 meter. The blade height is 0.12 meter and the shaft speed is 10,500 rpm. At the mean radius, the stage operates with a reaction of 50%, a flow coefficient of 0.7 and a stage loading coefficient of 2.5. Determine the relative and the absolute flow angles for the stage velocity at nozzle, static temperature and the pressure at the nozzle, assuming the efficiency of 0.96 and the mass flow. So this is the velocity triangle, everything. Okay. Stage loading is given by what? Okay. Is psi equal to delta H naught divided by u square equal to Pw3 plus W2 divided by u, a by u tan beta 3 plus tan what is Rx, dA by u tan beta 3 minus tan divided by 2. Okay, now I have to simplify this equation. Tan beta 3 is equal to psi by 2 plus r divided by CA by U, tan beta 2 psi by 2 minus R or Rx same. Okay, CA by U. Okay, what is CA by U? CA by U equal to what? Phi. What you do? Substitute the values. Substituting values of psi CA by U is equal to what? Phi and what? Rx. What is beta 3 now? Beta 3 here 68.2 degree and beta 2 is equal to 46.98 degree. Okay, so 50% reaction stage. For a 50% reaction stage, alpha 2 is equal to beta 3 is equal to 68.2 degree and alpha 3 is equal to beta 2 46.98 degree. Okay, at the mean radius Rm, so Rm is your what? Mean radius. Rm equal, what is, how to calculate Rm? 0.75 minus 0.12, 0.315 meter. Rate speed m is equal to 1050030 by 1315. Three 636 second. What is axial velocity? CA. So CA is equal to what? It's the axial velocity. CA equal to pi into UM. Okay. Solve it, we get 242.95 meter per second. Velocity at nozzle exit. P2 equal to CA by cos alpha 0.45 by cos. If you solve it, you get C2 as 652.5 86 meter per second. The static temperature at the nozzle exit. T2 equal to T02 minus T2 square divided by 2 Cp. $1200 minus 652.86 square divided by 11 T2 equal to 1016.3 Kelvin. What is the nozzle efficiency? Eta n is equal to H1 minus H2, H01 minus H2, H01 minus H2S. H2S is isentropic. Okay. Put in terms of temperature. Minus T2 by T01, 1 minus T2 by P01 to the power gamma minus 1 by gamma. Okay. So we need P2. Okay. So P2 by P01 gamma minus 1 by gamma, 1 minus P2 by 1. So if you solve it, you get P2 as, okay, this value you get 0.845. You solve P2, you get 1.986 bar. Okay, now you have P2. So I have to find out mass flow rate. M dot equal to rho 2 A2 CA is equal to P2 divided by RT2 into A2 into CA. Okay. Now if you substitute all the values, m dot equal to 1.986 into 10 to the power 5 divided by 287.1016.3, okay, into 0.2375 to 42.4. 31.9 kg per second. Okay, let's go to next question. A multi-stage axial turbine and with impulse stage operate with an inlet pressure and temperature of 6 bar and 900 Kelvin at outlet pressure of 1 bar. The isentropic efficiency of the are to have a nozzle outlet angle of 75 degree and the equal inlet and outlet rotor blade angles, mean blade speed to 250 meter per second and the axial velocity 150 meter per second, and is a constant across the turbine. Estimate the number of stages required for this turbine. So the velocity triangle, everything given in the question. Okay, if it is not given, you have to do it. Okay, let's solve it. So pressure ratio is known. Okay, so overall pressure ratio is what? Known. So T1 by T naught ES, okay, equal to T naught 1 divided by T naught E, gamma minus 1 by gamma 6, 0.33 by 1.33. So T naught ES will be your 576.9 Kelvin. Okay, so delta T overall, delta T naught overall, efficiency of the turbine, thermal efficiency T1 minus T naught ES 0.85, 900 minus 576.9, 274.6 Kelvin. Now from the velocity triangle, A2 equal to CA divided by cos alpha 2. What is CA? 150 cos 75, 579.5 meter per second. Okay, so what is T naught 2? T naught 2 is equal to T naught 1 minus C2 square divided by 2CP equal to 900 minus 579.5 square divided by 2 into 1148 equal to 753.7 Kelvin. Okay, so what is now Rx? Rx is what? Rx equal to what? 0. Okay, why? Because for impulse turbine, what? Degree of reaction Rx equal to 0. So Rx equal to H2 minus H3 divided by H01 minus H03 implies, okay, we know H2 equal to H3 now. Okay, because Rx equal to 0, that means what? This is 0. So H2 equal to H3 implies T2 equal to T3 because Cp is constant, 753.7 Kelvin. T2 equal to T3. Okay. From the velocity triangle at rotor entry, tan beta 2 equal to C2 sin alpha 2 minus U divided by Ca. Substitute all the values. 579.5 sin 75 minus 250 divided by 150. Value will be 2.065. Beta 2 64.16 degree. Okay. So now what is B2? B2 equal to Ca divided by cos beta 2 equal to 344.15 meter per second. B2 equal to B3 equal to C3 constant axial velocity okay. T03 is equal to T2 plus C3 square by 2Cp equal to 753.7 plus 344.14 square divided by 2 into 1148 equal to 805.28 Kelvin. Okay, so now the temperature drop for stage okay. T01 minus T03 is equal to 900 minus 805.28 94.7 Kelvin. So what is the number of stage formula? So the number of stages required for the turbine is delta T naught overall divided by T01 minus T03 equal to 74.6 divided by 90 94.7 is equal to 2.89. Okay, stage cannot be a decimal number, so let's take it as 3 stages. Okay, with these we can end the section. Okay, thank you very much for recording. Then you thank you very much. This is the last lecture of the section. Okay, you also watch the extra lecture that I already conducted from 5 to 6. There are some of the problems related to week 12 are also solved. Some of the concepts, some of the are already solved. Okay, and the last lecture of this subject, introduction to Airbreathing and Propulsion. Okay, last live discussion. For attending all the doubts, anything, ask. Effective weeks. Much.